Aloha Fide and aloha. Thank you all for joining us again today. Welcome to the third webinar in the Pacific Desk 2022 webinar series. I'm David Hitzel, the Pacific Desk Guam instructor. And today's topic of discussion is the application of the NOAA-Unique Combined Atmospheric Processing System, aka NUCAPS, to the tropical Pacific. Usual reminders before we begin: this is being recorded for educational and documentational purposes and will be posted simultaneously on Facebook Live. Please leave any questions in the comments section during the talk and include your location and affiliation. Questions can also be asked through Facebook Live or during a period of oral questioning at the end of each talk. But please otherwise refrain from having your video or audio switched on. And lastly, the video recording will be saved to view later on our Facebook page and/or YouTube. Okay, for upcoming webinars, the next webinar will be on the topic of global sea level rise. It is well documented that sea level is rising globally on average. However, there are subtleties related to where in the world it is rising fastest and at what rate, according to various model predictions. So our speaker will talk about those complications in the general sea level rise. And also looking at another webinar on tropical cyclones for July and one on hydrology and communications later in the summer. So today's panel, today's speakers are Brandon Eidlet, who is the newly minted Science and Operations Officer, or otherwise known as SU, at WFO Guam, where he has previously been the lead meteorologist since 2019 and a forecaster since 2010. He has also functioned as the Fire Weather Program Lead and Tropical Cyclone Program Assistant Lead during that time. Before that, from 2007 to 2010, he was a meteorologist for the Atmospheric Technology Services Company on Kwajalein in the Republic of the Marshall Islands, as well as working at the Missile Defense Test Launch Site, also there in the Marshall Islands. Brandon has a Bachelor of Science in Meteorology from North Carolina State University with specialization in broadcast journalism. He also has several graduate courses in tropical meteorology taken at the University of Guam. Brandon has functioned as a co-author in research pertaining to daily fire danger categorization on Guam, the fire weather program on Guam, and improved forecasting techniques for increased lead times of deep tropic convective hazards. He received the 2021 Regional NWS Isaac Klein Award for redesigning WFO Guam's Tropical Cyclone Workshop, and he is also an accomplished musician. Our second speaker today is Scott Lindstrom. He creates a variety of satellite-related training material for the National Weather Service out of the Cooperative Institute for Meteorological Satellite Studies, otherwise known as SIMS, in Madison, Wisconsin. He has the enviable task of looking at beautiful satellite imagery daily and sometimes blogs about what he sees at the SIMS satellite blog. He's been interested in NUCAPS profiles since first seeing a talk at GOES-R Readiness before the launch of GOES-R. He is especially happy when giving in-person training on Guam or in Pongo Pongo. Just to explain a little bit why we're having a talk on this subject today. So the importance of technologies like NUCAPS for island forecasting. Vertical profiles of the atmosphere are primarily acquired from radiosonde observations, as all our students well know. However, launching of the radiosonde requires a surface station, a boat, or a plane from which to drop the radiosonde. While mainland regions have a mesonet comprised of various surface stations, oceanic regions have a data void due to a lack of adequate launching sites. However, in the present era, where radiosonde observations are unavailable, satellite technologies are stepping in to fill the data void. And while the geostationary satellites originally offered mostly 2D information, the current polar orbiting satellites with microwave receiving antennae are being optimized to see vertical profiles of the atmosphere over many points of the globe. So in the data sparse tropical Pacific, NUCAPS profiles from polar orbiting satellites give vertical definition to geostationary satellite imagery, essentially filling the gaps both spatially and temporally with data, with sounding data being received at approximately 6-hour intervals. Hence, a satellite-derived SKU-T may be plotted at various locations within the satellite swath, providing forecasters a look at available moisture and instability, both within convective regions and upstream. This is useful not only in predicting weather outcomes associated with tropical cyclones, but under typical trade wind regimes as well. Okay, so with that, for the details, I will turn it over to our two speakers.
All right, so good morning, good afternoon, good evening, everybody. I'm going to share my screen real quick, and so Scott Lindstrom is going to lead off first, providing some background information on how the gridded NUCAPS and also the NUCAPS profiles are produced from the microwave polar orbiters. And so with that said, again, Scott Lindstrom visiting and presenting from SIMS at University of Wisconsin-Madison, and then myself here in Guam. So Scott, go ahead and take it.
Okay, just go to the next slide then. I thought I'd start with a little history of hyperspectral sounders. There are a bunch of polar orbiters up there that have different flavors of hyperspectral sounders. So the first one, Aqua, was actually launched 20 years ago today, May 4th. Here in the Western Hemisphere, it's still May 4th, 2002. So it's been up there for 20 years, and it carries AIRS and AMSU, so a infrared and a microwave sounder. MEDOP A was launched in 2006. B and C have since been launched, and that carries EASI, which is another kind of sounder, also infrared with 8,400 channels, and AMSU with the 15 channels. And then we have SUMI NPP and NOAA-20. SUMI NPP launched in 2011. That carries the cross-track infrared sounder with 1,300 channels, and the ATMS, a different kind of microwave sounder, the advanced technology microwave sounder with 22 channels. So there are these sounders up there in polar orbits. They're predictable overpasses. I mean, I like to say, if you know where today's overpass is, you know where tomorrow's is. It's just to the east and about 20 to 30 minutes earlier. Something like SUMI NPP has a repeat cycle about 5 1/3 days and an exact repeat cycle in 16 days. So if you know where NOAA-20 is today, you know where it's going to be in 16 days. And it's an exact remap. And what you get from all this data, all these different sounders give you profiles of temperature, that's the T, and moisture, which is the Q. And there are different ways of doing that. So let's go to the next slide. So initially, there was something called the AIRS algorithm team. That wasn't part of NOAA. So as you heard already, the N in NUCAPS is NOAA. But the AIRS algorithm team developed methods to take the AIRS water vapor channels to compute accurate profiles of temperature and moisture. So remember, this is using the AIRS instrument with 2,370 some channels. But NOAA wanted something. So NOAA, mostly with the work by Mitch Goldberg, Walter Wolf, and Chris Barnett, wanted to adapt the Aqua and the AIRS algorithm to MEDOP. So MEDOP was launched in 2006. Remember, SUMI NPP went up in 2011. So they adopted the Aqua AIRS algorithm to the MEDOP and EASI instrument. And that was then adopted to SUMI NPP after launch. But this is one of the challenges of a research project. You know, who's looking at the output? So in 2013 and 2014, NUCAPS, which by then had been implemented into SUMI NPP, was implemented into AWIPS. So it was a way to get the profiles in front of the forecasters. So it's all well and good for a researcher to create these profiles, and they look great, but if you can't see them operationally, people aren't going to use them. So this is just research to operations is a difficult process, and NUCAPS is an example of that. And what you really need is a champion who sits down with the forecasters, and Chris Barnett was the person who initially did that. So he was funded to create NUCAPS and to talk to forecasters about it. So now we have this operational profiling system for satellite data. Next slide, please. So NOAA-Unique combined atmospheric processing system. This is originally for SUMI NPP, so it was actually originally called the NOAA-Unique CRIS ATMS processing system. So you might still see that in old documents. If you want to click, I think they're generated using the information from CRIS and the ATMS. They're available from NOAA-20 and from the MEDOP series of polar orbiters. The availability is these satellites have equator crossing times at 0130 and 1330. That means different things for people living in different parts of the globe. Here in the middle of the country where I am, middle of the United States where I am, NOAA-20 is flying overhead around 6Z and 18Z. If you're in Guam, it's flying overhead around 0Z and 12Z. So it's nice here in the central part of the United States because I get radiosondes at some time other than 0 and 12Z. And it's nice in the Pacific Ocean because you get radiosondes or profiles where you otherwise have no data. Next slide, please. How are these profiles produced? I'm not going to go through this in very big detail because, well, I'm just not going to. But there's a regression that uses all of the sounder and microwave channels to figure out, we have all of this information, and you use regression coefficients that have been derived from past events to create a first guess field. And then a retrieval is done to create the final solution. This is done using a radiative transfer model that has 100 levels, which is way more levels than this system can resolve. So you're getting a very smooth profile, but you have 100 levels of that very smooth profile. Let's go to the next slide, please. This is just a little cartoon on how retrievals work. So those two boxes on the left, that's really looking at the regression output. Then you feed the regression output into a radiative transfer model to calculate the transmittance at the various wavelengths that you're observing as well. And then you can compare the two. And if they don't match, you modify both the profiles and the skin temperatures. And you do this iteratively until either it matches, in which case you have convergence and you have a good solution, or you have no match, or you go through this cycle too many times. That's one thing I don't know. I don't know how many times it goes through. Typically, it's usually less than 10, and it failed to converge. So we're looking for good data where it has converged, and where it fails to converge, you don't have very good data. Next slide, please.
We're listening to
it doesn't use all the channels. It doesn't use all the channels that are on the CRIS. It just uses a subset of them. So for the regression, it uses all of the channels. All of the channels on the CRIS are used to create this first guess field. But then during the retrieval, it doesn't use all 1,300 channels. It uses a subset of them. As it says here, the dots are color coded up on the figure on the top. So all those green points are channels that happen to be used for surface temperature, if the skies are clear. The blue dots are used for atmospheric temperature, and the red dots are used for water vapor. And they chose the channels they use particularly. So they want a channel that has a response to, for example, just water vapor. You don't want one that's sensitive to water vapor and to sulfur dioxide, for example. You just want a response from one particular gas, or just carbon dioxide, just ozone. And if you're in a region of the electromagnetic spectrum where you have sensitivity to more than one gas, they don't use that one. I'll go to the next slide, please. So what's the most useful information in NUCAPS profile? Mostly water vapor in the mid-troposphere. That's where you get the most added information. If you want to click again, I think I have something that comes in on top of this. So the strengths of a NUCAPS profile are gradients, how things are changing with time. If you want to find a specific value, a threshold value, for example, you can use NUCAPS for that. And, relevant for the ocean, it's giving you observations where otherwise you have none. But the vertical resolution is a lot smoother than radiosondes. A NUCAPS profile is looking at a volume of air for one thing, and a radiosonde is just sampling a point as it goes up. Next slide, please. So we have the degrees of freedom there. DOF is how many layers are resolved by NUCAPS data in the troposphere, and you see there are 4 to 6 layers of water vapor and 6 to 10 layers of temperature. So think of a very smooth profile. Let's go to the next slide, please. If you are working for the National Weather Service, you can see what these look like in AWIPS, and we have this color coding where green is the retrievals completed successfully, yellow, the infrared retrieval failed, and red dots are where the IR and microwave retrievals both failed. Typically, that's where it's raining. The red dots are typically where it's raining. Yellow dots are where it's mostly cloudy. Next slide, please. You'll notice you have all those dots with profiles at them. Imagine you're trying to find a specific value. Clicking on those, interrogating those individual dots is very laborious and time consuming. So what's done is the data are gridded. This was originally done using Polar to Grid, which is from the CSPP library, so community software processing package, community satellite processing package. Now it's done just using Python, some Python code that's within AWIPS. So you grid the data so you have these horizontal fields that are much easier to interrogate or much easier to view a lot of data at once than looking at the individual profiles. So I have some links there that show you where you can find these gridded NUCAPS fields online. Next slide, please. And they look, one of the nice things I like about this is just an example over the US where you can look for elevated mixed layers. And if you click, you'll see the next overpass, and you see where the elevated mixed layer has moved to, and click again. So these were some elevated mixed layers, click again, that were associated with severe weather over the United States. So it helps you identify regions, click again, where you might have severe weather from these elevated mixed layers. Go to the next slide. We're talking about the ocean now, and NUCAPS is actually much better over the ocean than over the land for 2 reasons mainly. First of all, ocean temperatures are not variable compared to what's happening over the land, and the ocean emissivity is very well known, so it's easier to approximate exactly what the surface is looking like. Tropical lapse rates are steeper. So when you're looking at the atmosphere from the top and you're trying to figure out what's going on at the bottom, that's a lot easier to do if you have a big lapse rate, because then there's a lot of difference between lower layer temperatures and upper layer temperatures. So it's easier to discriminate those temperatures of the different layers. And because the tropical troposphere is a little bit less variable, that profile you start with, the initial guess is going to be closer to what the final product is. So it's a little easier to converge. Next slide, please. So just a summary. Why don't you click a couple of times? I think we can look at everything at once. These are some of the things I talked about, and I will hand it over to Brendan. Now keep all these things in mind, kind of as a whirlwind walk through NUCAPS, but he's going to talk about what you can tell now when you have these NUCAPS profiles.
All right. Thank you so much, Scott. Appreciate it. Thanks for bearing with me as I control the slides from 8,000 miles away. Always keeps it interesting. So what I want to do is give a couple of case studies on how we at the National Weather Service in Guam have utilized the gridded NUCAPS and also the NUCAPS profiles. So I don't see, Scott did mention the gridded NUCAPS, which is just a combination of all the different profiles, looking at the different layers to look at a better depiction of the data. So let's move forward. And so for the first case, we're going to talk about a fair weather forecasting process in Micronesia. So are we dealing with wet weather, dry weather? The models want to show one thing, but what does the satellite-based data indicate? So we're going to take a look at Pohnpei, which is the island in the center. On top is the visible satellite imagery, and on the bottom is the infrared satellite imagery. So first of all, this is a case, we're looking at the case where the computer models had for a couple of days indicated wet weather developing as a trade wind disturbance moved in from Koshrai and shifted westward toward Pohnpei. As it happened, the forecast at the time showed showers and thunderstorms moving into Pohnpei in the next 12 to 18 hours. But there was a couple of things that we were looking at and noting in the NUCAPS data that gave us a little bit of a reason to reconsider some of the forecast timing. So we go forward, and this is the morphed imagery. This is the total precipitable water available from SIMS. This is showing that river of moisture that's flowing in over Koshrai, lighter to dark green. That is indicating water in excess of 2 inches of total precipitable water. Closer to Pohnpei, it's a little bit drier. That red line is indicating approximately 1.5 inches of precipitable water, which is relatively dry, speaking for the tropics. But you can ultimately see all that moisture is anchoring around Koshrai. The yellow arrows that are the smaller yellow arrows, that is indicating low-level moisture transport between 1,000 and 700 millibars. Sometimes I like to look at a couple of the layers between the surface, 850 millibars, or even the 925 millibars to see where that low-level moisture is really flowing. But ultimately, you see that moisture band gradually shifting westward toward Pohnpei, but not very quickly. So we'll move forward. Let's see what the grid and NUCAPS data shows. So this is taking a dissection of the multiple layers of the grid and NUCAPS based total precipitable water. Up on top is a 500 to 300 millibar layer. You can see that deeper moisture content across Koshrai, and then a nice gradient of much drier air to the north and west, including over Pohnpei. As you shift a little bit lower down into the atmosphere, 700 to 500 millibars, you see a little bit better definition of that moisture river that's anchored over Koshrai, and then still much drier toward Pohnpei. As we drop lower below 700 millibars and then closer to the surface, you see that plentiful tropical moisture that is quite consistent day to day across the lower tropical atmosphere. But really, if you were to look at this picture in a three-dimensional perspective, you'd probably see a little bit of a tilting of the moisture with widespread moisture in the very closest level to the surface. And then that gradient of the wet to dry starting to shift a little bit closer to Koshrai, leaving Pohnpei with deeper, dry conditions. So how does the atmosphere or the relative humidity look at the 500 and 700 millibar levels? It pretty much reflects much the same thing we saw in the precipitable water, with much moist conditions over Koshrai, and then same thing in a 700 millibar level. Pohnpei is well on the side of the dry side of that gradient. So let's take a look at the NUCAPS profiles. On the top left, you see the profiles as they are available in our AWIPS. That is the system that we use in the National Weather Service to pretty much accumulate all of the weather data from satellites, models, radar, and you can see the widespread number of profiles that are available at our fingertips. On the bottom right, that is the NASA Sport version of the data quality. So we're looking at the same thing from AWIPS and also from NASA Sport, the gridded version of the NUCAPS. If you remember where Scott had mentioned the green, yellow, and red, the green indicates good retrievals. The yellow is you're getting partial profiles. The infrared retrieval is flagged as not so good, and that's likely because of cloud cover. And then the red is indicating the likelihood of precipitation and therefore a bad profile. Now, one thing I like to do is look at the data quality with the context of either precipitable water in the background, as you see in the top left, or looking at it with the infrared or the visible satellite overlaid. And so you can see exactly what's contributing to those red and yellow profiles, where there's likely some precipitation around those red profiles, southwest of Koshrai. And then where the cloud cover is a little bit patchier, you're still getting some okay retrievals, but that IR retrieval is getting flagged. Now let's see what these profiles look like. So on the top right, on our AWIP systems, we're able to do a pop-up SQT. And basically we can click on any of these little profile dots, and it just flashes up a little pop-up screen with the sounding. Lower right, you can see that sounding also better depicted. Ultimately, what we're looking at is a very low, shallow layer, which is typical of the tropics, of course, with a low-level capping inversion and much drier air aloft. This is typical of the Micronesia and Marianas dry season. We always see that low-level moisture and then a capping inversion with much drier air above it. And ultimately, how did that compare with the nearby Rayob from Pompeii? Ultimately, you can see that capping inversion is very well indicated in the balloon sounding. And keep in mind, we're dealing with a much higher temporal and spatial resolution because the data is collected continuously with the radiosonde versus the layer smoothing that we see in the NUCAPS profiles. But really, the features are pretty well demonstrated in both soundings. And so we're looking at that capping inversion right about 800, around 800 millibar level, and then much drier air aloft. So how did all this factor into the forecast? If you look at the forecast discussion, the forecaster at the time took note of all these conditions available from the NUCAPS profiles and also the grid and NUCAPS, and ultimately decided to hold off on the arrival of the showers and thunderstorms for Pompeii, that this moisture was not coming in very quickly. And thus we've got a forecast for Pompeii that's actually going to be drier for the next day and even that night before moisture would eventually move in another 12 to 24 hours. So we'll keep moving forward and we're going to go into a more of a convective unstable pattern. And we're going to go a little bit higher in latitude to about 20 degrees north latitude. And we're going to look at a feature that is typical of the summer months. That would be between May, especially into June, July, and then in the early fall up until August or September, where we see the tropical upper tropospheric trough and cutoff lows that start to dominate the pattern. And sometimes these events can lead to some significant weather outbreaks. So we're looking at Wake Island. That is about 20 degrees north latitude. Wake Island is kind of at that border between the tropical lower latitudes and then the more baroclinic dominated higher latitudes. So at the infrared, there's not a whole lot to note, some cloud cover as we look at the water vapor imagery. For those of you joining from the South Pacific, I apologize for our weather patterns being backwards, but I'll have some stuff for you with the Southern Pacific shortly. But looking at the upper levels, we're looking at the water vapor. There's a couple of features that kind of demand my attention as a forecaster. One is that upper level trough that is kind of arching to the north of Wake Island, and then a couple areas of cutoff lows and increased vorticity. As a forecaster, I'm thinking what effects that would have on both the upper level winds, upper level divergence, but also the deepening of these upper level lows and how that could affect the upper level temperatures, and then ultimately the convective instability. So let me start out with a comparison. This is a standard dry season pattern look. We're looking at 300 millibar temperatures on the left. This is from the gridded NUCAPS. This is valid of January 9th, 2022, earlier this year. And then on the right is the 300 millibar height. So for the same time frame, we're looking at the dry season. There's not a whole lot of change with the 300 millibar temperature or the height for this time of year of the trade season. However, how do things look in July of 2021? So this is the date of that event. Well, there is that cutoff low, if you remember from the water vapor imagery. Across on the left, you see the 300 millibar temperature. There's a significant temperature depression near and just to the northwest of Wake Island, where we're seeing temperatures about 6 to 10 degrees Celsius cooler within that cutoff upper level low. Similarly, that's also reflected in the 300 millibar heights, where we're seeing about a 200 to 400 meter depression and that 300 millibar pressure height compared to the equatorial tropics farther to the south. Now let's look at the quality, just to get a kind of a understanding of what we're looking at. So Wake Island, there's not a whole lot of conditions or cloud cover that's affecting the profile quality. There's a little bit of showers to the west northwest of Wake Island. You're getting some of those red flags, and then of course over the deeper Micronesia, the lower latitudes, about 5 to 10 degrees north, there is some more activity with the intertropical convergence zone. Now you'll notice, compared to some of the later graphics, this one does not have any latitude longitudes. That has been implemented. It was added a couple months after this image was taken by the NASA Sport folks. They are very quick and responsive to request, and I have found them to be extremely helpful in answering my questions and also modifying some of these graphics to make them more usable for the Guam area of responsibility. So we'll go ahead and move forward. So let's take a look at the lapse rates. So I had mentioned the increasing instability with those upper higher temperature and depressions. So on the top, we're looking at the 700 to 500 millibar layer, the lapse rates. And so we're looking at green, we're looking at lapse rates of about 5 to 6 Celsius per kilometer, and then steeper lapse rates in the yellows. So we're looking at some increased instability from the southwest to the northwest of Wake Island. But the big question is there any type of convective trigger that could take advantage of this increased instability? So question we'll see if we can answer in just a few moments. As we're looking at the much deeper lapse rates, going from 850 to 300 millibars, you're starting to see a little bit kind of a refined area of those steeper lapse rates. We're looking at about 7, almost 8 degrees Celsius per kilometer, just to the west and northwest of Wake Island. And that's kind of in the same region where that upper level low was also found. As we look at the precipitable water, and you remember that Scott also mentioned what is really beneficial to assess with the grid and NUCAPS for the tropics. I really find the moisture details to be extremely useful. And so here we're looking at that dry wedge of air that's kind of flowing around that upper level low counterclockwise, coming in right to the northwest of Wake Island. Above 700 millibars, that dry wedge is shown very, very well. As you get lower in the atmosphere, below 700 millibars and close to the surface, we're still looking at the pretty high background moisture. And so not a lot of features to be noted, except for areas of plentiful moisture. And remember, the data quality was green for most of these areas because other than a few clouds, there was not much precipitation. So we're looking at some dry air wedging in and plentiful low-level moisture. And so we'll see, did this erupt in interesting. Relative humidity by pressure, 300 millibars top left, 500 millibars in the middle, and 700 millibars at the bottom. You're still seeing that dry wedge of air that is just kind of infusing into this region and just kind of adding to the convective instability. And really for the tropics, these type of patterns do give rise, in my opinion, to some of the better convective related outflow gusts, where you can get some really strong downdrafts when it gets down to the ocean surface. The concern would be strong gusty winds. So what panned out? So I've got 4 different satellite loops. On the left, we have the infrared, top left. We've got a wider view on the top right, and you can see a large, long-lasting MCS, mesoscale convective system that developed. And this thing lasted for well over 24 hours, which is quite rare in the tropics. Usually they kind of blow out, they lose their steam, they stabilize, but this one kept on moving. Low-level clouds showed the trade winds coming in from the east, moving west, and the upper level winds kind of zipping off to the east, eastward. And so this MCS kind of moved anomalous to the flow, really being felt by the shear. And in the bottom right, you see some of those outflow gusts that were pretty significant. The scatterometer for this morning had indicated the 50-kilometer resolution was indicating 25, 30 knot winds. So you can imagine on a much smaller scale, there were some pretty significant gusts produced out of the system. Fortunately, most of this was over the open waters. The core of lightning just missed Wake Island just to the west by just a couple of miles. Otherwise, that would have been kind of an exciting day to have been on Wake Island. So we'll move forward and see what is available in the South Pacific. A while back, Dave Hitzel had asked me if I would be interested in speaking with this. And knowing that the Pacific Desk has a large footprint across the South Pacific, I asked if the NASA support folks wouldn't mind creating a South Pacific domain. And sure enough, they were very happy to oblige. And so let's take a quick look at the South. So this was a video, kind of a loop that I saved the other day across the South Pacific and some of the island locations just for your bearing. So we see some drier air across the lower latitudes of the South Pacific tropics. And then we got this nice frontal boundary and a lot of moisture kind of extending from the Solomon Islands down to the north of New Zealand, and then extending out farther to the east and southeast. And then looks like a strong high pressure just to the east of New Zealand. As we move forward and take a look at the morphed, excuse me, this is tripping up on me. As we look at the total precipitable water available from SIMS, we see that moisture gradient, much drier air over and to the east of New Zealand, and then deeper moisture right around Fiji, Samoas, Solomon Islands, and Papua New Guinea. And then north of the equator, you can see where the ITCZ moisture is quite widespread and deep. So if you do not have these links, you're going to see some of these images come with a QR code. If you have a smartphone, feel free to hold your smartphone up to the monitor, and this QR code should get you to those web pages. Otherwise, I will also have the URLs included, and so you can pull this off of the Facebook playback later. So just a recap, David had also shown the global RAOB sites. This is what's available to us at National Weather Service. A number of RAOB sites indicated in blue with their data across the South Pacific, but ultimately, how do we fill in all this data sparse region with data? NUCAPS can do that. And so the hashed green line, that is roughly the domain of the South Pacific region that Grid and Nuke, the NASA support page, provides for us now. And so we're going to go through a couple of the images just to see what is available and how we can kind of add to our insight of these patterns. So first of all, gridded NUCAPS via NASA SPORT. SPORT stands for Short-Term Prediction Research and Transition Center. On the top right, you can see a QR code and then a URL to the left. And ultimately, if you go to this page, you're going to see a time selection window. You can drop down and see the most recent passes. Right now, there's not a whole lot of them. There's been a couple of anomalies in some of the data acquisition and displaying. So some of them are the older data files do not show up in this time list. For Guam domain, you can actually go back into mid 2021, I believe. And so you can see all those different passes. So if there's a case study that you want to look at, to investigate across your area, this is a good page to pull up some of the older information. The second pull down menu is the domain. So here we've got indicated the South Pacific domain, and this is the single pass that is available at this time. For this domain, you'll probably see three full passes within a 4 to 6 hour period. And so this is the descending pass. You're going to see a descending pass, and then 12 hours later, the ascending pass as the satellite orbit passes around the other half of the day. So how does the data quality compare? Well, on the left, you see where all that cloud cover exists, north of New Zealand, also to the west. And then similarly, the data quality, you're seeing a lot of bad retrievals. The IR retrievals are somewhat hindered with the yellow, and then both the microwave and the IR retrievals are bad because of all the precipitation, especially in these heavier convective cells. So that agrees quite well. And farther to the south, you see some yellow indicators. So some bad infrared retrievals, and probably related to this the low-level strata-Q that you see dominated in this high-pressure region east of New Zealand. So some of the other images we can look at is the precipitable water. Here we have the top layer precipitable water from 500 to 300 millibars. You can see that gradient of deeper moisture in the upper levels, and then much drier conditions east of New Zealand. Additionally, across, excuse me for my lack of familiarity with the islands, around 10 south between the equator and 20 south, much drier air aloft. So ultimately, that agrees well with what we're seeing in the satellite imagery. We're going to drop a little bit lower into the atmosphere, and now we're seeing a lot higher moisture content in the atmosphere, still sharp gradient along this frontal boundary. And then even at the 850 to 700 millibar level, you see the difference between the higher latitudes and then that of the tropical latitudes, where you have that abundant and plentiful moisture on most days. And then finally, in the very low levels, there's more moisture available, of course, especially in this convective happy area extending across the Solomons and New Caledonia and then eastward. Looking at the RH, the 300 millibar relative humidity, you see that difference of very dry and the tropical equatorial area, dry air aloft, and then also east of New Zealand, where that high pressure was dominant. And then there's that convective moisture all present in that level, and there's that cloud cover is being pushed and moisture being pushed into the upper atmosphere. And now we're dropping through the atmosphere down to 500 millibar levels. The same features are quite well preserved. Still dry air east of New Zealand, aloft of that high pressure system. And then even at the 700 millibar level, and then the 850 millibar level, you can still see that tropical moisture in the very low levels. It's just not kicking up much convection, as you saw in a satellite earlier. Now, one thing I want to mention is here's the temperature at 300 millibars. You're seeing that contrast in conditions with the higher, the warmer temperatures at 300 millibars in the tropical latitudes, and then much cooler conditions south of 30 degrees south. So there is that difference between the tropical air mass and the baroclinic air mass. And as a comparison, the 300 millibar heights, you're seeing that difference in conditions with the much higher 300 millibar pressure level and much lower in the southern hemisphere. I did not include it here, but the grid of NUCAPS does also give you provide a tropopause height image. And so you would see much the same thing in this case, where you got a much higher tropical troposphere height, and then or tropopause height, and then a lower tropopause in the higher latitudes. Looking at the 850 millibar temperature, you're still seeing that gradient along that convective feature, where you've got cooler temperatures south of 25 south, and then much warmer tropical air mass to the north. And before I move to the next page, I just want to remind you, you'll see that I've got 4 passes, 3 passes of the NUCAPS data. all in one. This is just, I took 3 images of each pass, 1, 2, 3, and then combined that. And that is why the date time group is kind of garbled. I just composited 3 images onto one. So can you, from the South Pacific or outside of the National Weather Service, can you access the profiles? Yes, you can. And there's a couple of different options. One is via the NOAA Office of Satellite and Product Operations. So you go to this link, and then you will see a map. And so it's a little bit slow to get it to process just right. So you just had to be patient and trust that you're doing the right thing. So what you first do to get some NUCAPS profiles is you want to click on this square dot right here. And so that gives you a drawing option. You will then kind of left click on your mouse and just drag out to a small area. And over here on the right, you're going to see a small grid that I think it populated about 10 to 15 seconds after I drew the square. It's pulling in all the available NUCAPS profiles, and the color coding is indicating the relative age of these profiles. Once you click on one of those grid points, it's going to take you to another page where you can see the past 20 days of NUCAPS profiles. And it's going to be showing you if you've got a good retrieval, good profile, or not so good a profile. In this case, we've got a good profile. It shows accepted. And then you have several different lines based on the inputs. And so in this case, we've got a good profile. Everything looks agreeable. It looks great. And then you got a profile that was rejected. So both the microwave and the IR had bad retrievals, did not converge on a solution. And likely this is because of precipitation in the area. And you can see just kind of how that sounding looked. If you're looking at this data in AWIPS, as I often do, you're going to see crossing temperature and dew point lines, and just meteorologically does not make sense. And so that's what it looks like. So user beware, know what the data quality is, and then you know better how to use it. In one of Scott's slides, there was a little caveat that mentioned that even with bad retrievals, some of the higher level data is still quite useful, especially for aviation purposes. So there's also a couple other options. We've not investigated those in depth here at the National Weather Service, although some Weather Service offices have investigated this avenue. But this is another program, a Python program that you can load on your computers. Some information included in the URL or also the QR code on how you can get this program, and then you can be able to obtain the profiles. And then also a quick look guide for additional explanations. Also, for more information, Scott Lindstrom and a couple others over at SIMS, they have a daily satellite blog where they put a lot of useful information about NUCAPS data, how to interpret and some case events, but also other satellite data, including the SIMS, TPW, and many other satellite-based products. So if you ever get a chance, if you want a quick read on some very informative topics, go to the SIMS satellite blog. They update this just about every day. And so you will never find a better place just to find great information on how to use these new and cutting edge satellite tools. And so with that, I will go ahead and wrap it up. And so I just want to open it up for any questions. Feel free to chime in. And with that, I will turn it over to David.
Okay, yeah, so I'll give everybody a chance to ask their questions before I ask mine. So feel free to unmute, or you can ask through chat if you like.
Hi, this is Tom Dunn calling. Question?
Sure.
Yeah, out here in the University of Hawaii, do you have many, have there been some studies or use of the gridded data assimilated into model predictions for forecasting? Kind of in an operational sense.
I think I'll let Scott answer that one. I will have a tentative answer, but Scott will probably answer much fuller.
I don't know about that, but no, the answer is no. The data from the polar orbiters, like from the cross-track infrared sounder and the ATMS on NOAA-20, those data are directly assimilated into the numerical models. It's not gridded first and then assimilated. It's assimilated in its raw form.
Okay.
So it's not even create. I mean, the NUCAPS profiles are not assimilated. The data that goes into the NUCAPS profiles are assimilated.
Okay. Any other questions? Okay, so one of my first questions was where to find these materials outside of AWIPS, but I think you did a pretty good job of explaining that. And I copied most of the links to the chat section. So if you have access, you can look at them right now and bookmark them. And I hope in the future, this will become a tool that's included in Pacific Desk training, because I think it's particularly useful for the Pacific or just anywhere oceanic. So hopefully in the future, we'll go more into detail and give you sort of practice exercises so you can become proficient like Brandon. So I guess my question, maybe this is more for Scott. I'm interested in using this for research. And so I'm wondering if what Brandon talked about is more for like a operational use and sort of a real time. But I'm wondering if you use this for research, is there any improvement on resolution that you can get? Are there any plans in the near future that the vertical resolution may improve with this? Because when I was reading about this, I thought, maybe one day, maybe this will replace balloon soundings. Like if the resolution becomes good enough, and they definitely are better in terms of how much horizontal resolution they can cover. So is there any better vertical resolution that you can get nowadays for research? And is the vertical resolution is it going to improve in the future? Or is there some sort of limitation to the instruments?
I would say the vertical resolution is limited by the number of bands that are on the satellite. Mm-hmm. So, in theory, I would think that EASI would have the best vertical resolution because it has the most spectral bands. I don't know if that's the case or not. So NUCAPS profiles will not suddenly have better vertical resolution because you have that limit from the CRIS in just how much you can resolve looking down into a semi-transparent, occasionally opaque atmosphere from the top. So I'll also say the climatologist in me just cringes when I hear people say, I want to get rid of radiosondes because I like long-term data, long-term data records. So yeah, I don't think in the next 30 years, radiosondes will not be replaced. Now, of course, there is with GeoXO, which is the next generation geostationary satellite from the US, they are planning on flying a geostationary sounder. Currently, that's being planned. So the GXS, I believe it's called. which will have a instrument that's similar to EASI or CRIS. I'm not sure of the vertical, I'm not sure of the discretization and the I mean, how many channels it will be observing. But that'll be nice because it'll give you global coverage hourly versus these swaths that give you great information over the ocean, but it's not there all the time. So I don't know if that answered your question.
More or
I think
less.
that the short answer is no, you will not get finer detail with the present suite of polar orbiting sounders that are up there.
Mhm. Okay.
I suppose you could do some machine learning maybe and tease more information out, but
Okay. Yeah, because like Brandon was saying, there's smoothing in the sounding, but it might be nice to see the details too, because you can spot high cloudiness, mid-level cloudiness, with some of those details.
Yeah, for me, the biggest thing that I get out of it is looking for those gradients, looking for those moisture gradients, especially as they're moving through. Once you look at the moisture details and you apply it along with the wind details that you're seeing in the models, or even with the sims to mimic TPW and some of the other moisture products, it really beefs up your insight into what the situation is doing, and especially if you're looking at the potential for some flooding rainfall events and looking at those converging winds and where that moisture content is, especially in the layers.
Okay.
Thanks, Scott.
Okay, so last chance for questions. Anyone else? Okay, then I'm going to thank our speakers, Brandon and Scott, for a great talk. And thank you, Brandon, for including the South Pacific. Sometimes we don't get both perspectives, so that was really nice to see. Okay, so I'm gonna sign off there. So
You
good to see
take
everybody.
care.
Thank you.
thank you.